Discrete random variables, page 3. Number 9. A bag contains 5 blue and 3 green tickets, and a number of tickets are randomly selected without replacement. We let X denote the number of blue tickets selected. Find the probability distribution of X if 2 tickets are randomly selected and if 3 tickets are randomly selected. Well, if 2 tickets are randomly selected, the different outcomes are 0 blue tickets, 1 blue ticket, and 2 blue tickets. So what's the probability that we're going to get 0 blue tickets? That would be if we get 2 green tickets. So that would be like GG, right? Green would be 3/8 times 3/8. What's the probability that we would get 2 blue tickets? It would be 5/8 times 5/8. And what's the probability that we would get 1 blue and 1 green? Well, basically it would be 5/8 times 3/8, but you need to remember that there's 2 ways of getting it. You could get GB or you could get BG. So we could say it would be 2 times that. Okay. What's the probability distribution for 3 tickets? Okay, so in this case it's going to be 0, 1, 2, and 3. And the probabilities are going to be, okay, so this is 3 greens. The probability of getting 3 greens is, and remember it's without replacement, it's going to be 3/8 cubed, right? What's the probability that you're going to get 3 blues? It's going to be 5/8 cubed. Okay, what about the probability that you're going to get 1 green and 2 blues? 1 green and 2 blues. That would be green and then blue 5/8 squared. But remember, there's more than one way to get that. In fact, there's 3 ways to get it. And then there's a little bit of symmetry here, and this one is like that. Okay? And you can figure that out. If this is too fast for you, what you do is you go, okay, I'm going to figure out every single possibility. There's green, green, green. There's actually 3 different ways of getting 1 blue. It would be blue, green, green. There's green, blue, green. And there's green, green, blue. Those are 3 possibilities each. And so that would total up to that one there. So there's 3 possibilities to get 1 blue and 2 greens. Okay? Alright, moving on. Number 11. When a pair of dice is rolled, N denotes the difference between the numbers on the top faces. Display the possible results in a table. Whenever you have 2 dice being rolled, the best thing to do is to draw that grid that we drew before. We're going to draw a grid that has 6 lines this way and draw 6 lines this way, and each one of these intersections represents an outcome. So this is going to be like the red dice, 1, 2, 3, 4, 5, 6, and then we'll do the blue dice, 1, 2, 3, 4, 5, 6. Okay, and let's see. We're going to make a table which shows the difference between the faces shown. So the difference could be 0, 1, 2, 3, 4, 5. Can the difference between 6? No, because like even if you have a 6 showing on one dice, the smallest number you could show on the other dice is 1. So the biggest difference you can show is 5, right? And then the probability. Okay, so we're going to figure out the probability for each one of these differences. So what's the probability that the difference between the 2 dice is 0? So that would be when you roll 2 6s, when you roll 2 5s, 2 4s, 2 3s, 2 2s, 2 1s. If you roll any of those combinations, you got 0 difference between the 2 dice. So I'm going to put here that there are 6 ways of doing that. Okay, what about the different ways of having one a difference of 1 showing. So that would be 2 versus 1, 1 versus 2, 3 versus 2, 2 versus 3, 4 versus 3, 3 versus 4, etc., etc. Do you see the pattern here? So then this is 1, 2, 3, 4, 5 times 2, it's 10. There's 10 ways of doing that. Okay? What about the different ways of showing a difference of 5? Okay, so that would be a 6 versus 1 and a 1 versus 6. There's only 2 ways of doing that. Okay? What about the different ways of showing a difference of 4? That would be 5 versus 1, 6 versus 2, 2 versus 6, 1 versus 5. So there's 4 ways of doing that. Okay, what about the different ways of showing a difference of 2? So that would be 3 versus 1, 4 versus 2, 5 versus 3, etc. So that would be 2 times 4, which is 8. Okay. And what about the different ways of showing a difference of 3? That would be 4 versus 1, 5 versus 2, 6 versus 3. So it would be 3 times 2, which is 6. Okay. And then we just add up all those different possibilities. We already know it's 36, so we can put divided by 36 for each one. So each one of these has the denominator is 36. Okay. So now we've done the probability distribution table. Find the probability that n is equal to 3. So that would be that, right? So the probability that n is equal to 3 would be 6 divided by 36, also known as the 1/6. Find the probability that n is greater than or equal to 3, and this symbol here means or. Oh no, it means given that. So probability of n is greater than or equal to 3, given that n is greater than or equal to 2. So the probability that, remember that to figure out the conditional probability like this is the same thing as saying that the probability of both happening, okay, A intersect B, divided by the probability of B happening is that's how you figure it out. So the probability that B is going to happen is this, okay? So what is the probability that n is greater than or equal to 1? That would be all of these added together, which would give you 30 divided by 36. So I'm going to write that down here, 30 divided by 36. What about the probability that both A and B happen, which is that n is greater than or equal to 3 and n is greater than or equal to 1? So that would be this part here. That would be 1236, which is 1/3. Okay, I'll write 1236 here. And then if you divide that out, you end up with 12 divided by 30 because the 36's cancel out, right? 12 divided by 30. So it's going to be 12 divided by 30. That can be reduced, of course, but no big deal. You can leave that. It's equal to what, 6/15? All right. Moving on to part C. Expectation. Expectation has a special mathematical meaning. It kind of means average or mean. So let's look at this. If you roll a dice 120 times, how many times do you expect to roll a 6? You know, from your intuition, you would probably say that you would roll a 6 1/6 of the time, and 1/6 of 120 is 20, so you would say 20. How did you calculate that? Well, we basically took 120 and we divided by 1/6, or we multiplied times 1/6 because we thought that the probability of getting a 6 is 1/6. Okay. How do you calculate expected value of x from the outcomes x and the corresponding probabilities p? Actually, you do exactly what you did here. You're going to take the outcome and you're going to multiply it times the probability. And then actually you're going to add them all together. Okay? So let's move on here. If a game is fair, what is the expected gain? If you're in a casino and if the casino wasn't trying to make money off of you, then the games would be completely fair to both sides, and then on average you would not make money and you would not lose money. So the expected value in a fair game is 0. Okay? Actually, the expected value in a game in a casino is against you. In every single game, they have a well-known way of getting more money from you than an average of 0. Your average is going to be negative something. Okay. In a particular region, the probability that it will rain on any one day is 0.28. On how many days of the year would you expect it to rain? Okay, so I would say that that would be 365 days in the year times 0.28 probability that it's going to rain on any one day. Okay. 3. If 2 dice are rolled simultaneously 180 times, on how many occasions would you expect to get a double? We expect to get a double, and if you look at our grid here, you expect to get a double 6 out of 36 times. Okay, so the probability we're looking at here is 6 over 36. Okay, and if we roll 180 times, we're expecting to get 1/6 of those to be doubles. Okay. And during the snow season, there is a 3/7 probability of snow falling on any particular day. If Udo skis for 5 weeks, on how many days could he expect to see snow falling? So it would be 3/7 is the probability. And 5 weeks is equivalent to 35 days, right? So it would be about that. 7. In a random survey of her electorate, politician A discovers the residents' voting intentions in relation to herself and her 2 opponents B and C. The results are indicated alongside. Estimate the probability that a randomly chosen voter in the electorate will vote for A, B, or C. Okay, well that's pretty easy. All we need to do is add all these up, right? I'm going to do this on the offline calculator. 165 plus 87 plus 48, 300 total. Okay, so the probability that they're going to vote for A is 165 divided by 300. Probability that they'll vote for B is 87 over 300. And the probability that they'll vote for C is 48 divided by 300. Okay. If there are 7,500 people in the electorate, how many of these would you expect to vote for each one of these? So you're just going to take the probability that you calculated above, and you're going to multiply it times 7,500 in each case. 7,500, 7,500. Okay. Oops. 7,500, and this is going to be 48 divided by 300. Okay. That's it. On to page 4. A person rolls a normal 6-sided dice and wins the number of euros shown on the face. Find the expected return from one roll of the dice. Okay. So, you would say you're going to add up 6 probabilities, or 6 expected values. If you get a 6, you get 6 reais, 6 euros. So you're going to get 6 euros 1/6 of the time. You're going to get 5 euros 1/6 of the time. You're going to get 4 euros 1/6 of the time. You're going to get 3 euros 1/6 of the time. 2 euros 1/6 of the time. And 1 euro 1/6 of the time. Okay? Basically, that's going to add up to 21/6. Okay? Which is 3.5. That's kind of expected, right? 3.5 is halfway between 1 and 6. So. Find the expected gain of the player if it costs 4 euros to play the game. Would you advise the person to play several games? it costs €4 to play the game. So if it costs €4 to play the game, then he's going to pay 4, and then he's going to get an expected value of 3.5. So basically each turn he's getting an expected value of negative 0.5. So would you advise to play several games? No, right? Okay. Suppose it costs k euros to play the game. What value of k would result in a fair game, and what value of k would result in a profit being made by the vendor? The value of k that would result in a fair game would be 3.5. If it costs exactly 3.5 to play and the expected value on each turn is 3.5, then your expected value is 0, and that would be a fair game. What value of k would result in a profit being made by the vendor? K is greater than 3.5, right? Anything greater than 3.5 and you would have an expected value slightly more than 3.5 or much more than 3.5, or much more than 0, I'm sorry. 11. A country exports crayfish to overseas markets. The buyers are prepared to pay high prices when the crayfish arrive still alive. If X is the number of deaths per dozen crayfish, the probability distribution for X is given by the following. Find K, and over a long period, what is the mean number of deaths per dozen crayfish? Okay. So, again, what they're looking for here is they want to add up all these numbers and they want to get a value of 1, right? So let's add up all the numbers that besides k and see how much that is. 0.54 plus 0.26 plus 0.15 plus 0.01 plus 0.01 plus 0.00. Okay, so 0.97. So k has to be 0.03. Okay. Over a long period, what is the mean number of deaths per dozen crayfish? Okay. So in this case, we're going to do similar to what we did above. The probability that you're going to have 0 deaths is 0.54. The probability that you're going to have 1 death is 0.26. The probability that you're going to have 2 deaths is 0.15. The probability you're going to have 3 deaths is 0.03. The probability that you're going to have 4 deaths is 0.01. And the probability that you're going to have 5 deaths is 0.01. Okay? So let's put this in the calculator, and then I'll tell you how much that is. I typed in all these terms. Let's add them all up. 0.74. So 0.74 is the mean number of deaths per dozen crayfish. 13. A pair of dice is rolled and the random variable m is the larger of two numbers that are shown uppermost, or the value of a single die if a double is thrown. In table form, obtain the probability distribution of m. B. Find the mean of the m distribution. Okay, as I've been preaching, whenever you have a problem where you roll 2 dice, it's better to draw the grid so you can see all the possibilities. So, looking at all these combinations of blue and red dice rolls, how many of these is going to result in a 6, where the maximum value is 6 on both rolls? That would be these 6 and these 5 additional ones. So, the probability that you're going to show, or the different combinations that will give you a maximum of 6 would be anytime the blue rolls 6 and anytime the red rolls 6. So that's 11 possibilities. Okay, so that would be the different ways of getting a maximum value of 6. And then we're going to go all the way down. Okay. All right. And so what about 5? How many different ways of showing getting a maximum of 5 are there? Well, there's these 5 plus these 4, so it's 9. What about 4? 4 would be these 4 and these 3, 7. See the pattern now? Now, maximum dice space showing 3. It would be 5. And so on. So this would be 3 and this would be 1, right? And each one has 36 possibilities, of course, because it's 2 dice rolls. Okay. Now they're going to ask us expected value, right? They ask us for the mean of the M distribution. This is the table form of the probability distribution. Find the mean. The way you find the mean, of course, is to multiply all the x's times all the p's, etc. So you're going to multiply 6 times 1136. You're going to multiply 5 times 936, etc. And then you're going to get a number there. Now this is kind of a pain to type in the calculator, so let me show you what I did. I did it in Excel. Someday in your life you are going to appreciate all that Excel can do for you. Look how I made these series of numbers pretty easily by just extending them. So I have 6, 5, 4, 3, 2, 1. I have the pattern that I noticed there in the probabilities. I have them all divided by 36. I calculated the p-value for each one, and I do that just by copying all the cells. I multiply the x times the p for each one. Here I get that, and then I press the magic button to sum them all up. I get 4.47. Okay, so let's come back. All right, so the answer is 4.47. That is the mean value shown. So, you know, when you roll a dice, the mean value shown by a dice is going to be 3.5 because that's halfway in between 1 and 6. But if you roll 2 dice, the mean value shown by both dice together is going to be 4.47. Okay? All right. Moving on toward the end here. 23D, binomial distribution. Binomial probability distribution is applied to sampling with replacement. Okay? When we have replacement, the probability for success is always the same. Random variable x is the total number of successes in n trials. Probability of success is constant and is denoted by p. Probability of failure, of course, is 1 minus p. Okay, here we refer to the spinner on page 619. For those of you who don't happen to be looking at the book, this is what the spinner looks like. It's got 3/4 of the area that is blue, 1/4 of the area is white. What's the probability that the spinner is going to land in blue? 3/4. What's the probability that the spinner is going to land in white? 1/4. Okay. So what is the probability if you spin 3 times that you're going to get 3 spins in blue? That would be 3/4 times 3/4 times 3/4. Right? Okay. What's the probability that you're going to get 3 whites? It's going to be 1/4 times 1/4 times 1/4, or 1/4 cubed. Okay. What's the probability that you are going to get 2 spins in blue and 1 spin in white? Well, you have to be careful here, because it's not just going to be 3/4 times 3/4 times 1/4, because you could get blue, white, white, or I'm sorry, blue, blue, you could get blue, blue, white, you could get blue, white, blue, or you could get white, blue, blue. So there's 3 ways of getting that. So you have to multiply the 3/4, 3/4, 1/4 by 3, because there's 3 ways of that happening, right? Same thing with this one, except instead it's going to be 3 times 1/4 times 3/4 times 3/4. Okay, since there's 3 ways of getting that result, you need to multiply by 3. Okay, and if you multiply all these out, you will find that they add up to 1 magically. All right, maybe not so magically. Number 1, expand p plus q to the 4th, and you're like, oh my gosh, not this again. Yes, this again. Okay, hopefully all that experience you've had between last year and this year has made it so that this really means something to you. I'm doing this without even explaining to you what I'm doing. Hopefully you'll remember. Okay, so basically the pattern is Pascal's triangle, 1, 4, 6, 4, 1. How do I know I use 4? Because of that 4 there. Then I'm going to do p to the 4th, p to the 3rd, p squared, p to the 1st, p 0. Then I'm going to do q to the 0. Oh, q to the 0, that's 1. So I'm going to erase it there. Okay, and then q to the first, q squared, q cubed, and q to the fourth. And then I'm going to add them all together. Okay, so I've expanded p plus q to the fourth. Now you're saying, why the heck did we do that? Next part says, if a coin is tossed 4 times, what is the probability of getting 3 heads? Okay, the probability of getting 3 heads if a coin is tossed 4 times is, let's see, how many ways are there of getting 3 heads if you toss 4 times? There's head, 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 tails. There's head, head, tails, head. And there's head, tails, head, head. And there's tails, head, head, head. So the probability of getting 3 heads should be 4 times probability of getting head times the probability of not getting head. Okay? And, probability of getting head should be cubed, right? Probability of getting head times probability of getting head times probability of getting head times the probability of not getting head. Now, do you see a pattern here? This looks like that, doesn't it? Okay? So that is why binomial expansion is so related to binomial probability. All right. And by the way, P for tossing a coin is a half. So it's 4 times 1/2 cubed times 1 minus half, which is also a half. Okay, so it's actually 4 times 1/2 to the 4th, which is 4 over 16, which is 1/4, by the way. Okay. Now it says expand 2/3 plus 1/3 to the 4th. And so now we're going to write the exact same thing. We're just going to use that, right? Except now we're going to use 2/3 and 1/3. So it's going to be 2/3 to the 4th plus 2/3 to the 3rd plus 2/3 to the 2nd plus 2/3 to the 1st plus 1. And then in the opposite direction, we're going to be doing 1/3. So 1/3 to the 0, so there's no 1/3 there. 1/3 to the 1, 1/3 to the squared, 1/3 to the 3rd, and 1/3 to the 4th. And then we're going to put our Pascal's triangle coefficients here. It's going to be 1, 4, 6, 4, 1. We don't need these ones here, do they? Okay. And we're done. Okay, that's part A. Then part B, it says, 4 chocolates are selected at random with replacement from a box which contains strawberry cream and almond centers in the ratio 2:1. Find the probability of getting all strawberry creams. Okay, so all strawberry creams, let's see, the probability of getting a strawberry cream is 2:1. Actually, that you could say that would be a probability of 2/3, right? 2:1 is actually 2/3 to 1/3. So 2/3, right? So the probability we're looking at here, P is equal to 2/3. Probability of success is 2/3. Okay? And then it says, find the probability of getting all strawberry creams. There's only one way of getting all strawberry creams on 4 selections. That would be this one here. All strawberry creams would be that one, right? What about 2 of each type? 2 of each type. So that would be getting 2 strawberry creams and 2 not strawberry creams. There's 6 ways of that happening. It's right here. Okay? See, 2 and 2. 2 successes and 2 failures. What is the probability that you would get at least 2 strawberry creams? At least 2 strawberry creams. That's a little bit more difficult. At least 2 strawberry creams. That would be the all strawberry creams. That would be 3 strawberry creams and 1 not strawberry cream. And that would be 2 strawberry creams and not 2 strawberry creams. And not these 2. Okay? So you could multiply all that out. But the important thing is you know which terms result in which of the successes.